Good day, people. My name is Mashau Azwihangwisi. I'm from the University of Venda. I'm doing Masters in Agricultural Economics. I'll be giving you a short talk on introduction to modeling. In this talk, I'll cover the introduction, types of modeling, and lastly, conclusion. In the hierarchy of models used in HPWs, this tool doesn't fall under any approach. It diverges from the hierarchy of models and it gives you something different. So I hope you're gonna enjoy. Now, what is a model? Whenever we talk about a model, many people think of different things. Some think of a beauty pageant. Some people will think of a brand new Ferrari, a new model which Ferrari has made, a BMW or a Benz, and some people, the climatologist will think of modeling of the climate system. So a model is a three-dimension or simplified representation of an idea, structure, or an object. But there's something which you must keep in mind. All models are wrong, but some are useful. This statement I will elaborate on it later. So just bear in mind that all models are wrong, but some are useful. Now let's look at the types of model. We have the mathematical model, scientific model, conceptual model, physical, and other models. Now, what are the elements of a model? A model must provide equation, which the equation will describe the behavior of a system, structure, or an idea. Like I said, a model is a simple or a better explanation of an idea, system, or a structure. So a model must provide equation to the equations which will describe the behavior of such system, idea, or a structure. It must also provide a framework of solving such equations. Now, let's look at the example of a model. If you can check, we have two different views of the earth here. On the left, we have the flat earth. This is the flat earth. And on the right, we have the spherical earth. This is a simple and a better explanation or a 3D dimension view of the earth. This is the spherical earth and this is the flat earth. But both of them, they are representing what? The earth. But they are representing the earth into different shapes. So this is a better explanation of a model. A model is a simple or a better explanation of an idea, object, or a system. Here, our example is an earth system. An earth system has been shown in two phases, in a flat earth and in a spherical earth. Remember, I said all models are wrong, but some are useful. Now, let's look at these two pictures. We have the spherical earth here, and we have the flat earth here. If you can check closely, this one, it shows us air circulations, but this one shows us a better view of how many continents we have and how our continents situated. If you can check here, we cannot easily diagnose how our continents are situated, but here we can tell, here it's Canada, here it's Russian Federation, but here we cannot tell how the air circulates, but here we can tell how the air circulates, which simply means that this one is useful on disclosing how our continents are situated, and this one is useful on disclosing how the air circulates around the earth. But both of them, like I said, all models are wrong, but they are useful. Here, this one is useful in disclosing the continents and this one is useful in showing us how the air circulates. Now, let's look at modeling. The activity Modeling is an activity of making a particular part or a future easy to quantify, define, simulate, or understand. If you look at the two previous examples where I was showing you that all models are wrong but some are useful, and the example of a model, these ones, it's easy to understand them. It's easy to visualize how the earth is situated and how the shape of the earth is what it is. But here, and you can easily quantify, and that's what modeling does. But with modeling, we need a modeling process. And in a modeling process, we have three phases. The first one is model development, and the second one is simulation, and the third one is analysis. Now, we have a real world problem here. Now, we need to develop a model to solve the real world problem. And when we develop a model, we need to make approximations and parameterizations to validate our model. And we need to make numerical resolutions to verify our model. And then we'll have a developed model. After developing our model, we'll have to establish our model so that we can get our results. And when we get the results, we'll have to analyze those results. And after analyzing those results, we'll test for validation. Are they valid or not? And when we are done, we'll make conclusions as to do we have and after making conclusions, we'll validate. And then after that, we'll have a solved or unsolved problem. If we have a solved problem, we'll go to the real world and face the problem. But here is the issue. If we have unsolved problem, we go back to the model development and come with other strategies, come with other types of models on how we can solve the real world problem. Now, let's look at this example. We have a situation here. Here at HPW, we are concerned. We are worried why this earth is habitable. And I went and choose one model that the earth is habitable because it's too cold, or it's too hot. It's not too hot or not too cold. And then after developing my model, after making approximations and parameterizations, I develop a model which is not too hot or not too cold. And then after I establish my model, and then I get the results. And the result said, due to the location in the solar system, the earth is not too hot and not too cold. Now, after that, I have my results. I make analyze the results that I have, and then test for validation. Are they valid or not? And then after that, I make conclusion. If you can check closely here, we have some whitish things, which I assume that it's snow, and we have some green here, green grasses here, and then we have water. We have my friend here who's not even wearing a jersey, showing that the earth is not too cold or not too hot. Now that we know that the earth is not too hot and not too cold, and then after conclusion, we have a solved problem now. Since we have a solved problem, we go to the real problem and tell people, no, the earth is habitable because it's not too hot or not too cold. But for somebody who got the wrong answer, we'll go back to the hierarchy of models and have to choose one of the models there. Like I said, we need to make parameterizations. Parameterizations it's the process of defining and deciding the parameters which are necessary for a complete or relevant specification of a model. We need parameters which are necessary for a complete or relevant specification of a model. Let's take a look at this picture. If you look at this picture here, you cannot tell if the person is a male or a female, but you can tell that it's a human being, right? But we need those parameters which can help us to make relevant or complete specification that this person is a male or a female. Now, if you look at the bigger picture here, we have the private part here, and we have the chest. Now we can tell that from the look of the private part, you can tell that this is a male, and look at the chest, you can tell what this is a female. There are no breasts, and these are parameters which are necessary for us to make a complete or relevant specification. Now let's look at approximations. For us to make approximations, we need a approximation is a value or a quantity that is nearly but not the exact, not the correct, but the exact value or quantity. Let's look at this picture here. Someone can say circumference over diameter is equal or approximately 3.14. It's what? Equal or approximately. But somebody can say it's approximately because here, if you can look at this picture, this is not a circle. It looks like what? An oval. But for somebody who's saying is circumference over diameter is equal to 3.14, you can easily go against that person. But for somebody who's saying what? Approximately, you can easily what? Develop a model. It's not exactly, it's approximately. Keep that in mind. Now let's look at the importance of modeling. Modeling helps us to visualize a system as it is or as we want it to be. It helps us document the decision that we have made. It gives us the template that guides us for constructing what? A system. And it permits us to specify the structure or behavior of a system. Now let's look at the principles of modeling. Every model can be expressed at a different level of precision. The best models are connected to reality. Let me take you back to the example that I gave you. If you look at the flat earth and the spherical earth, if you look above your head, you will see clouds. But when you look, if you're standing on top of the mountain, you will see everything under, like below you. You will see everything flat. You won't even see where the earth ends, but you will see something on top of your head, which is connected to reality that the earth is spherical or the earth is flat. But remember, those models are useful in their own ways. So, in regard to this, all models are connected to reality. Somebody can say, I can see where the earth will end, or I can't see I can see something above my head. Those people are making assumptions which are connected to reality. They are modeling and making models which are connected to reality. No single model or a view which is, no single model or a view which is insufficient. The choice of what model create has a profound influence on how the problem is attacked and how the solution is shaped. If you check on the example that I gave you, why the earth is habitable, we experience winters and summers, which means the earth is not too hot, it's not too cold. Since we're experiencing what? Both. We experience hot and coldness, but in different what? Times. So that helps us or influence on how the problem is attacked and how the solution is shaped. Now, in conclusion, all models are wrong, but some are useful because all models are developed for a particular purpose. Keep that in mind. And a model is what we perceive it to be. I thank you for listening to me. Until we meet next time, ciao.